So we're going to look at the following example now. We're going to consider the solid region bounded by the plane z equals my function f of xy, which will be 2 minus x minus 2y, and the 3 coordinate planes. So if you graph this function right here, z equals this is the equation of a plane. And so you're going to have a plane, and you want to consider the intersection of that plane with the 3 coordinate planes, so the xy plane, the yz plane, and the xz plane. So if I draw this out here, if I look at the intersection with the z-axis, so here x and y are 0, then z is 2, so we get 0, 0, 2. If we look at the point on the y-axis, so remember this is x, this is y, this is z. If x and z are 0, then y is at most 1, so y is 1, so 0, 1, 0. And then if I'm looking at the point on the x-axis, so y and z are 0, which means x is 2. So 2, 0, 0 would be my point. And so here you're going to get this kind of triangular region, but then this is going to be a filled in region, so you want the region between the 3 coordinate planes, so between here and here and here, but also between this triangle that you have plane there. So this is my solid region here, and what we're going to do is we're going to take a vertical cross section parallel to the YZ plane. So if I take something parallel here to the YZ plane, then I'm going to get this triangular region here. So I get this is a triangular region. And for me to find the area of a triangle, I just need the base and the height. So if we look at the base of this triangle, the base is on the XY plane, and so Z is 0. And I'm going to solve for Y here, because that's going to be the length of my base. So this length right here, that's Y. So I'm going to solve for Y in my equation. 2y equals 2 minus x. Y is 2 minus x over 2. And now let's look at the height. So here, if I'm looking at the height, It's right here. So I'm on the x-axis, which means here y is 0. So if you plug in y equals 0 into your equation, you'll get z equals 2 minus x. And z represents the height here because z is our vertical distance right there, z. So here, I've now got the base, and I've got the base, and I've got the height. So I can look at the area of this triangular cross section. So it solely depends on the variable x. And remember, area for a triangle, it's 1/2 base times height. So AX, it's 1/2. The base we said was 2 minus x over 2. The height was 2 minus x. So in the end, this area will be 2 minus x squared over 4. And now we need to add up all of the areas of these cross sections. So you're going to find volume, the volume of the solid, you're going to compute the integral from a to b of a of x dx. And if I look back at my region, what did x go between? X went between 0 and the maximum was 2. So here the volume will be the integral from 0 to 2 of 2 minus x squared over 4 dx. So you're going to have to do either FOIL the top out, or you can do u substitution here. If I do u substitution, I'll get a negative 2 minus x cubed over 12. Plug in 0 and 2. So if you plug in 2, you'll get 0 minus a negative, so it'll be positive 2 cubed over 12, 8 over 12, or 2/3. But we're going to go back to our picture of our region and look at things a little bit differently. Okay, so remember I'll just kind of roughly sketch it again. Right, I had this triangular region here. And instead, what we're going to do is we're considering y before to be constant. When we took our cross section, y was a fixed number. But what you can do is you can also consider x to be constant. So a fixed value of x So here, now I'm looking at these cross sections this way instead. So here I'm looking at something parallel to the XZ plane now. So if we look at this triangular region, let's separate it out into an image on its own. Let's say I'm saying y is 0 here. sorry, not y equals 0. So the height here of this triangle is given by z 2 minus x minus 2y, and y is going to range from 0 to 2 minus x over 2. So in this way, we can get a of x is the integral from 0 to 2 minus x over 2. So now we're getting 2 minus xy minus y squared over 2 there. And if you plug this in, you'll see you get the same formula you did before for a of x. And so what this means is I can think about volume here as being this double integral over my region R. And so I can think about volume here as being the integral from 0 to 2, 0 to 2 minus x over 2, 2 minus x minus 2y dy dx, which we computed this earlier to be 2/3. But now, instead of thinking about volume as being really a single integral, which is what we had earlier, you can really think about volume here as being a double integral.